dear friends. We welcome you today on our channel and the Project Creative Society. We're glad to introduce you our speaker, Lior Shamir, who is Associate Professor at the Kansas State University. Hello, Dr. Shamir.
Hello, thanks for having me.
Dr. Shamir, could you please tell us about yourself and why did you pick your area of research?
I'm an Associate Professor at Kansas State University. And the research that you asked about, it's something I've been working on for about 10 years now. And the reason, it's hard to know the specific reason for getting into specific research. We explore the research and get into the where we find the most interesting observations that drags us in and let us explore more of that. But the reason I've been working on it for so many time on something so specific is that the observation is rather provocative. It changes something, some conceptions, some existing conceptions that we have about the universe. And we need to make sure that it's solid, that it's based on sound science, that it's not driven by some error or some observational biases and things like that. And it involves a lot of data. It involves 5 different telescopes that I use to make sure that all telescopes show the same thing, and each telescope is a large number of galaxies. Each telescope gives us hundreds of thousands of galaxies. We combine them to over 1 million galaxies, but we need to make sure that it's consistent. So that takes time. And once you see something with one telescope, you want to know that what you see is you're convinced that it's true, that is the universe that we see from Earth. And that drags you into more data. And when you get more data, you analyze more data, and maybe you start to see different things that you didn't see before when you analyze so much data. And you get to see that what you saw before was just the beginning. Maybe there's more, and there is more, and I'll be happy to tell you about that.
Thank you very much. It's interesting. And the second question is, according to your works, you are dealing with the issues of the origin of the universe. How long have you been doing this, and what conclusions do you have about the official Big Bang theory?
Right. So in the past 10 years, I've been working on that. And if you go to the conclusions, then what we see here, first of all, we see that the universe is not completely random, as some of my colleagues tend to believe. There's something that we call the cosmological principle. It's a working assumption that has not been proven, but that is the working assumption for almost all modern cosmological theories, and it means that the universe is completely random. Wherever we are in the universe, or whatever direction we look at in the universe, we're going to see about the same thing because everything is randomly distributed inside the universe. And my research shows that that's not necessarily the case. The universe has a certain pattern. It's not completely random, and we see it also in other probes. Right now, it's not just my research that shows it. We see other probes that are showing that the universe is not random. Specifically, what my research shows is that not just the universe is not random. When you go deeper in the universe, which means back in time, we see that the universe was even more structured. The structure was even more defined when the universe was younger, and that leads us to the idea, to the contention that when the universe started, it didn't start randomly. And perhaps what the data shows, that it is possible that the universe started when it was rotating as it started, which means that perhaps an external force was acting on the universe when it started. So one of the explanations could be that could be something more than the universe. There could be maybe multiverse, many universes, could be other things that it's not, I don't want to make any conclusions right now, but it looks like, and it shows that there are other forces that were acting on the universe when the universe started. And I'd be happy to tell you more details about how that conclusion is made.
Yes, I would be happy to hear details, and we would be interested to know more about the model of the universe that you understand. And we also interested what position in the planet Earth occupies in this model, and
Right.
what is the location of the Milky Way Galaxy in relation to the center of the universe, if you can.
Exactly. That's fantastic questions. So, and let's see by that. So, what the probe that I'm using, the piece of information that I'm using is spiral galaxies. Now, spiral galaxies are a unique astrophysical object in the sense that they have perspective. And by perspective, I mean that a spiral galaxy would look different. Depends on the angle of the observer. So if you look straight, and you can see in the screen, you can see a spiral galaxy. It looks like to be rotating clockwise if you stand in front of it. If you go an observer standing behind the same galaxy, it would look to be rotating counterclockwise. So the galaxy is the same galaxy, but it would look different based on the position of the person observing it. And that's what makes that object so special. And that feature allows us, or makes that probe suitable for understanding the geometry of the universe better. Many other probes won't give us that piece of information. For instance, a star, just like the sun, whatever, the way you look at it would look like a star, would look the same. Spiral galaxies are different. And what we can do, and one of the things is that if the universe was completely random, then we expect to see an even number, more or less even number of galaxies that rotate clockwise and galaxies that rotate counterclockwise should be about even, because if everything is random and we take 100,000 galaxies that spin one way and 100,000 galaxies that spin any other way, it should be about roughly the same, not exactly the same, but statistically the same. And but now when we have robotic telescopes, we can actually test if that assumption is indeed true. And what we see is, first of all, that the number of galaxies that spin each way is not the same in different directions, in all directions that we look at. If we look one way, we'll have more counterclockwise galaxies. If we look the opposite way, we see that we have more galaxies spinning counterclockwise. And it's very consistent, and that's what creates a pattern. And that pattern, because it depends on the perspective, it also allows us to answer the question that you asked: where is the universe? Where is the Earth? Or where is the Milky Way compared to the rest of the universe? And first of all, it's not in a completely random place in the universe, as we tend to think. The Earth has is in a certain definable place in the universe, depends on that piece of information. It could be hard to tell right now, but it could be very close to its center. Maybe this center, maybe not exactly the center, but close to it. My most recent calculations show an estimated distance of about 300 megaparsecs. That's about, let's say, 1 billion light years. So it looks like a lot, but in cosmological terms, this is just right around the corner, 1 billion light years. And and the other thing is that the pattern tends to be stronger when we go back in time, because more distant galaxies are. The light coming from these galaxies came way longer than the time now. If we use the Hubble Space Telescope several billion years ago. So we actually see the universe as it existed several billion years ago, and the universe that we see from several billion years ago is has stronger patterns and is more definable than the universe that we have now. So the universe, if we continue with that trend, it means that the universe started as something definable and then became gradually more chaotic as time passed.
What is actually in the center of the universe? And is there a special radiation from the center of the universe that you have observed?
Well, okay, it's a good question, but I don't study if you talk about radiation, maybe you mean the cosmic microwave background, which is radiation, very old radiation starting just relatively shortly after the Big Bang. And it's one of the evidence for the Big Bang, the cosmic microwave background. So that is something that I don't do personally. There are several satellites that collecting the data, but I can compare my data with the data from the cosmic microwave background. And one interesting thing about the cosmic microwave background is the cold spot, CMB, what's called the CMB cold spot. So we expect that if the universe is completely random, we expect the cosmic microwave background to be randomly distributed. And we see some evidence that it's not randomly distributed. And the source of it is still in discussion, whether it's cosmological or maybe something that affects maybe the obstruction of our own galaxy or something like that. But there's one thing that is the cold spot, one spot in the universe that is colder than everything else. And statistically, it wasn't expected to be there. There's like 1 or 2% statistically to have that by chance. So we need to think that that cold spot there's something real about it. It does exist, and we should consider it as something real. Scientists do try to analyze it, do try to see what is more special about that spot that is not special in everything else in the universe, because we have 3 satellites, the COBE, the Planck, WIMAP, that show all the same thing. All of them show that one spot in the universe is colder than everything else. And how it is related to my observation, and I can show you in the, let's see, there it is. So here you see that's data from all telescopes combined, about 1 million galaxies. So I combined here it's just 3 telescopes, not 5, 4 telescopes, 4 telescopes combined together, about 1 million galaxies here. And it shows that the patterns of where the axis of the pattern peaks is very close to that CMB cold spot, very, very close. Statistically, it's basically identical. And that is an interesting thing. It may be one of the first things that shows something special about the cold spot. That's where galaxies tend to be more aligned in the directions of their spin. And until now, scientists looked at the population of galaxies. Maybe the population there is less dense, and that's why that spot is colder. But it was found that the density of the galaxies is about the same as everywhere else in the sky. But the alignment in the rotation, in the direction of rotation of the galaxies, that is not the same apparently. In that cold spot, the galaxies tend to be more aligned, and there's still no direct explanation, but that's the one thing that shows something unique about that CMB cold spot. That's the entire sky that we see from Earth. And what the chart shows, what we see in the sky, is the significance of an axis that starts at that point in the sky, a cosmological scale axis. So these are each spot, each point here is computed with about 1 million galaxies, and the computational process determines the probability of the galaxies, if we're centered at that spot, the galaxies to be all aligned in the entire universe that is observed here. And we can see that it peaks at the CMB cold spot here. And it's done by what's called cosine dependence. We fit the spin direction of the galaxy into a cosine dependence to see statistically where it's most likely to happen.
You talk about the axis of the galaxies, and I think that these axes influence on each other, and these galaxies influence to each other too. So, and as we know, in the center of the in the galaxy, we have two bubble, as like the researchers say, that is Fermi bubbles, yes, and. Could you please explain how these bubbles influence to each other from different galaxies?
Okay, yeah, that's a good question. And that is pretty much a mystery, because I'll tell you why. Because we know that within galaxy clusters, there's alignment in the spin direction of galaxies, and we might think that it's related to gravity because a galaxy cluster, though the galaxies inside it might interact gravitationally with each other, and we explained that recent also within filaments, so the universe is made of clusters and filaments, and galaxies within filaments also tend to rotate, to be aligned in the way they rotate. And again, we can assume that because they're gravitationally interacting with each other. The thing is about my research and a few other studies that were done is that those galaxies tend to be aligned in their spin direction, even if they're way too far from each other to interact gravitationally. So it's not the gravitation that make them spin. What does make them spin in a uniform way? That's a mystery. That's a mystery, and there's no explanation. It looks like it's happening, and we see that also in other astronomical objects, sometimes in quasars, although in quasar it's maybe less obvious, but we see that also in other astronomical objects. They tend to spin in a uniform way that is not explained right now. And that's why we need more research to understand these things.
Thank you so much. And is there a generally accepted opinion about whether the universe is expanding, and if it's infinite or finite, stationary or not? What is your understanding of that?
Well, I'm not. That's another good question that I'm not sure I have a perfect answer to. The universe does seem to be expanding. It's not my research. I didn't do that research. From what I see, the universe does seem to be expanding. The steady state theory of the universe is not very common. It's hard to make a strong case that our universe is in steady state. The universe is changing. That's what it looks like from what we know right now. And for my research, I actually go back in time. I don't go forward in time. I haven't thought about that really, what we can conclude about the future of that. But I cannot make, with my research, I cannot make a really strong statement of whether the universe is expanding or not, or whether it's steady state or not. It does look actually from my research that the universe does change over time. The early universe is not the same. Also in other probes, also in my observations, the early universe was more uniform, was more had more stronger, more definable patterns than the current universe. And it looks like the universe, for my research, it looks like the universe is becoming more chaotic over time.
My question is, do you think the universe develops cyclically? So there's a pattern of processes that from birth to finish. And have you seen any cyclical developments outside our galaxy, or maybe which could reflect onto what's happening in our solar system? Any similarities between galaxies themselves and any numbers in cycles, maybe 12,000 years, 24,000 years, anything?
Cycles. That's another good point. And it wasn't necessarily my interpretation of my own research. That's the interpretation of other people interpreting my research, which I tend to take it seriously. Which is an indication that the universe is actually rotating. Now, if the universe is rotating, then we have cycles in the rotation. And the idea of rotating universe, that concept started, I believe, in the 1940s. But that idea was associated with a steady state universe, and was neglected for some time. Then now we have that rotating universe theory coming back again because of many observations that the current models don't fully understand. So we start to look back into some models of rotating and expanding universe, and we have some cosmological models like that. They're not considered mainstream cosmological models, but that doesn't make them less correct than the mainstream, than the models that we do consider as mainstream. So an idea of rotating universe can be very much related to cycles. And by the way, we just recently figured out that filaments, for instance, have rotating features in them. And that's another cycle, maybe in a less, far smaller scale than the rotating universe. But we see that things rotate that we didn't know before they're rotating. And rotation and cycles are very much aligned with each other. We can make a very clear link between something that rotates and something and changes and cyclical changes. And the most basic example is the Earth rotating around the sun, which is related to the seasons that we have. Obviously, that's a way oversimplified example, but it's basically based on the same idea.
I like that you mentioned that you focus on the history of the past and not the future. And that's one of our questions is, why is it so important to know how our universe was formed? Have you tried to compare your research with chronicles, ancient manuscripts? Have you tried to refute or compare and contrast and find any type of facts related to the universe formation?
Okay, well, you're asking really good questions that really relate to, that actually pushed me a little bit outside of my comfort zone. My comfort zone is observations and things that I can quantify. And it's good that you push me and you need to push, we as a scientific community, we need to be pushed out of our comfort zone probably more often than we do, and understand, for instance, why, like you asked the good question, why do we do these things? And I guess it's related to the natural curiosity of us as a species to know what our origin is, where do we live? What is this place we're living in? So we see what we can see around us, but as we have more instruments, we can see more, and that drives our curiosity further. What is this place that we live in? What can we know about it? And what other information can it tell us about it? And if you talk about ancient manuscript, then the history of human history has been always like that. We've always wondered about our place in the universe, and it changed based on the instrumentations that we had. So if we thought that we have just one planet, there's just one planet in the universe, which is the Earth that we live in, then and there's just one star, which is the sun. There's just one sun, and then we learned that the other stars that we see in the sky are suns, and then we thought that we had just one. And those stars make a galaxy. We learned that they make a galaxy. And then we thought that the galaxy, that's the universe is made of just this galaxy. And that wasn't that long ago. That was at the time when we have good technology. Like we had cars and airplanes and radio and TV, and we had all that technology. And we believed that the universe is made of just one galaxy. And that was an argument made by pretty clever people who insisted that we have just one galaxy in the universe, although we had telescopes, strong telescope, and we could see thousands or maybe hundreds of thousands of galaxies in the sky. And we insisted that these are not galaxies, these are clouds inside our galaxy that may look like galaxies, but they're not real galaxies. And we insisted that the universe is made of just the Milky Way. And then it changes when we learned that these are actually more galaxies. The universe is much bigger than we thought in the past. The universe, again, surprised us because one of the arguments to say that what we see in the telescope are not galaxies is that if we believe that these things are galaxies, that means that the universe is too big. That would be crazy. But who defines crazy here when we talk about the universe? And the universe, again, surprised us and taught us some humility. And if we go to the ancient manuscripts, so these people, maybe they did not have the instruments that we have today, but they had their own intuition. They had their intuition, and the intuition cannot be, also, we cannot underestimate, and we cannot just reject their intuition compared to our intuition, because we use also now a lot of intuition. We tend to claim that everything is based on hard facts, but it isn't really. A lot of intuition, all of the cosmological models are not proven models. These are assumptions. These are theories and none of them has really been proven. We don't have one proven solid cosmological model. Even if we say that sometimes we say that we do, or we claim that we do. We had those models in the past, and we learned that they were not even near what the universe is. So I don't underestimate the intuition of those ancient scholars who tried to figure out the universe at that time. The idea that, for instance, one of the things that they did, that the universe started at a certain point, that was the intuition of ancient people in the past. And that idea was rejected by scientists for many years. And many scientists, like Einstein, for instance, thought that at a certain point that there's a steady state universe. The universe has always been here and will always be. Ancient scholars thought that there was some point when the universe started. And apparently, according to what we know right now, Big Bang theory, that is not exactly, but that's the same contention that the ancient scholars exactly follow the intuition of the ancient scholars, that there was a point where everything started. The universe hasn't always been here and will not be here forever. And that is in agreement with the ancient scholars. Now, we can go back to the theory where the Earth is at the center of the universe or close to the center of the universe. Some ancient scholar proposed that idea. That idea was rejected by Copernicus, by Copernicus, I believe, who claimed that the Earth is at a random place in the universe, yet without providing any proof to that. We use that as an assumption. We don't have a proof to that. And my research, as well as other evidence from for instance, the cosmic microwave background, show that the Earth might not be in just random place in the universe. It might be at a defined place in the universe. Some say it might be at the center of the universe. I tend to somewhat agree with that. It could be, and it could be that the Earth is not at the center, but fairly close to the center of the universe. So that intuition of ancient scholars that the Earth is at the center of the universe was rejected and still largely rejected. But I don't think for a good reason. We need to find the proof. We need to be open-minded about it. Their intuition might have been correct, and we have some evidence showing that. And we need to look at that seriously and with an open mind. And maybe in the past 300-400 years, we were not fully correct about it.
Yes, and we know that astronomers use gravitation lenses, and we would like to know how do they serve for researching, and what is it, gravitational lenses?
Okay, that's I don't study gravitational lenses other than looking for gravitational lenses. They're not very common. So part of my research is developing those algorithms to find gravitational lenses in the sky. Again, you need to be lucky to have that. So a gravitational lens, if you ask, is we know that mass can have a distortion effect on light, and a galaxy has enough mass to distort the light, and it creates the same effect as lenses. And then you can see galaxies that are way more distant, but you can see them as if they were magnified, as if you look at them through a telescope. But the galaxies need to be aligned in a very special way, and it needs to be a good coincidence to have that. And until 2 decades ago, it was considered as something theoretical that will never happen. It was considered a theoretical idea that is unlikely to happen. Now we know that it does happen because we see them. So we accept the idea that we do have them. And sometimes we see the magnified galaxies like distorted. So they're a little bit curved, or a lot curved. But gravitational lenses, that's a tool that allows us to observe more distant galaxies that we cannot see, that we often cannot see in the telescopes that we have now. But they're pretty rare. It's difficult to make conclusion of cosmological scale based on gravitational lenses because we don't have that many of them. Different robotic telescopes. Now we have robotic telescopes that image the sky every night, all night, keep collecting data, keep imaging the sky. And they have very large databases of galaxies, of images of galaxies. And that allows us to show if the spin direction of the galaxies is randomly distributed. Can galaxy decide to randomly to spin that way or another way, or how is the decision made by a galaxy, whether it's random or whether there's some pattern to that. And that is done. To do that, and we need to use some computing to annotate all these galaxies. Obviously, it's impossible to have manually start annotating millions and millions of galaxies and see which ones we can identify the spin direction. So we need to use computers for that, and computers are also more objective in doing that. So that is done by annotating each galaxy. So we have a computer program that can tell us for each galaxy if it spins one way or the other. Once we have a lot of data, we can compare different telescopes. Here are just 3 telescopes, comparison of 3 telescopes, but all telescopes, all of those 3 show the same thing. They show that the galaxies, the spin direction of galaxies is not randomly distributed. There is a pattern in that, and the pattern is such that it makes an axis. So the spin direction of galaxies are distributed in the universe in the form of a certain axis, and the universe might be oriented around an axis like that. We can see also here that's from one telescope called the Sloan Digital Sky Survey, but that's a relatively small data, 64,000 galaxies, but it's large enough to make statistical analysis. And we can see also here that because we know also the distance of these galaxies from Earth, we can see that the signal gets stronger as we go farther from Earth, which means back in time. So the early universe was more uniform than the current universe. We can also see it here. That's the Hubble Space Telescope and the relatively distant galaxy from the Sloan Digital Sky Survey. So the Hubble Space Telescope obviously can look far deeper in space. And we can see similar patterns. So what we can see here, that's the map of the sky. And for each point in the sky, we can tell where the most likely axis is, the axis of the distribution of these galaxies. And we can see that those telescopes are in fairly good agreement with each other, given the statistical noise and given some statistical error that we have. That's as close as we can expect it to be. And these are 2 different telescopes, 2 completely different telescopes. That's another experiment. Again, 2 telescopes. One is the dark energy camera. The other is a telescope called Pan-STARRS. Again, 2 telescopes, 2 completely different set of galaxies, both showing the same pattern, the same distribution of galaxies in the universe. And when you have 4, now 5 telescopes showing the same thing, then you might think that maybe the consistency shows that there is something real going on here. And that shows that the peak of the axis is aligned very close to the cosmic microwave background cold spot. There's a cold spot in the cosmic microwave background. We don't know why it's cold, why the temperature there is lower, but we know that it's there. There's no explanation to that because if the universe is random, it's not supposed to exist. But probably it does exist. 3 different telescopes saw it. It's pretty consistent, so it does exist. And the spin direction, the alignment and spin direction of the galaxy peaks exactly at that spot. Whether it's a coincidence, maybe it's a coincidence. We don't know. But that's something that should be taken into consideration. There are a lot of theories about that cold spot. Some suggest that the cold spot, that's the pathway to another universe. That's how we go to a different universe. I don't know. I have no opinion about that theory, though it is interesting. And that's why there are plenty of reasons why it's not an error. And every possible error has been studied and fully analyzed to make sure that what we see is the real thing that we see. That's the real universe that we see from Earth. either flipping the galaxies, randomizing them, testing the data manually. Some of the data are manually is annotated manually just to make sure that the manually annotated data is exactly agrees with the computer annotated data. So that is not an error. That's the universe that we see from Earth.
Thank you so much. And can you one more time explain that model as an egg, what that colors means?
So the color means stronger probability that there's an axis there. So we fit the distribution of all the spin directions of all the galaxies that we have. In this case, it's about 800,000. In the previous example, it was over 1 million. So we fit them statistically into what's called cosine dependence. And we see from each point in the sky, we go with the computer, we go point by point, and we compute the probability that such an axis centered there by chance, could be centered there by chance. And what we see is that it's a very clear pattern. Red color, as you see, that's the what you see here in the right, that's the scale in sigma. That's the statistical probability. That's a statistical strength that an axis exists there. And it goes to very high probability, 4.4 sigma, which is basically very, very unrealistically to happen by chance, a very high statistical probability. But that's what the colors show. And so if we tend to think that there's an axis at around the right ascension, that's the sky coordinates 300 and declination 0, for instance, there's a low probability, very low probability that an axis goes there in the distribution of the spin direction of the galaxies. But if you go to more or less where the cold spot is, that coincides with the that you see a redder color. It's more red, and that means much higher probability of an axis that peaks there. And that probability is actually, we can consider it certain. It's so high that we consider it certain that there's an axis that goes right there and goes through the CMB cold spot.
Thank you. And have you observed or you know something about certain force or certain energy that influences the course of the planet and transforms stars?
Okay, about stars, no, I did not look at stars, but you mentioned you did mention energy, and that is, and in cosmology, energy has an important role. There's a term called dark energy. Now, dark energy, the term is, probably, in my opinion, it's one of the most deceiving terms in science to call something dark energy, because there's nothing really dark in that dark energy, nothing that I can see dark. It's that energy is as real as any other energy, according to the physics that we know. How it impacts us or the universe in general, that is still to be figured out. We know that the universe is accelerating. The expansion of the universe is accelerating. Energy is coming from some way, from somewhere. We call it dark, not because it's dark. It does exist. We call it dark because we don't know where it's coming from. And sometimes we say dark energy and dark matter like it's on the same, like it's the same level. But that is deceiving, like I said, because the meaning of the word dark, when you say dark matter, it has completely different meaning than when we use it with dark energy. And if we tie to my own research, then if the universe was indeed born spinning, then some energy had to act on the universe and have some influence on it to create that effect. Where is that energy coming from? Same thing as dark energy. We don't know where it's coming from. And how it affects everything else, again, that's something to figure out, but it's something very tricky. It's not dark, it's real. It's not necessarily a theoretical energy, it's an observed energy, and we have to accept that observation. But we don't know where it's coming from. Yeah, it's easy to put in an equation of the universe. When we make a model of the universe, it's easy to put in an equation of something that's dark and it fills up the equation, so it scores the equation and everything works. But that's really the easy way. The scientific way is to understand where it's coming from, and we cannot really make an assumption saying, "Oh, it's dark," and we need to understand where it's coming from. We really need to and understand how it impacts us and how it impacts the universe. So there's a lot to do on that front, for sure. One thing that we can learn from cosmology is humility, because cosmology, we always thought, has in the entire documented human history, we always thought that we know what the universe is about. And every time we were sure of that, and we're very sure of that, and we tend to ignore other people, maybe others who disagreed with us, and so on. That every time it happened, we were completely wrong. We weren't even close. And every time we thought that we figured out what the universe is, the universe taught us some humility and showed us that none of what we said was anywhere near what the universe is. And that is one lesson that we can take. We might think we're sure of something. We might think we know. We have to remember we might be wrong. And in some cases, we need to think we're likely wrong. Where are we wrong? What did we do that is wrong? And again, what I'm showing you right now, that's the universe that we see from Earth. I can only tell you what we can see. I cannot tell you what the concept of the universe is. That is still yet to figure out. We're collecting the evidence, we're collecting the information piece by piece, and it takes apparently hundreds of years to do that. And we still don't know, or not even close to understanding the concept of the universe and what the universe is.
Shamir, we truly appreciate for you being part of this project, Science and Creative Society. And we are volunteers of the Project Creative Society, and our project is created by people from all over the world. From 180 countries, we have volunteers who are actively trying to change the format of the society, from the consumer one, where money is the highest value, to the creative one, where human life is the highest value, where creative ideology predominates everything, and where science can actually become an open-minded science where everybody could understand it in a simple and easy terms. So we truly appreciate you being part of this interview. And may we ask you a question? As a Creative Society project, what is your vision of science and creative society? How can science actually serve people, and how can science actually improve human lives?
Well, it's a broad question. Many things that science can improve human lives in, making us think what our purpose is, what our role is in the place we're living in, what is our making us think more beyond the consumer end and how to survive, but also why to survive and what it means to survive, what it means to be a part of the human species and to be part of this universe that we live in. The meaning of things. Is there meaning to what we do beyond just consuming, beyond just staying alive and living our lives? What's beyond that? What's more than that? And these are the things that we need to think of. Otherwise, I'm not sure there is a point in being in our survival if we don't look for the reasons, for the meaning of the things. Again, you're taking me outside of my comfort zone. It's not something that I can prove. It's not something that I have data and it comes down to the statistical probability or p-value or things like that. So that takes me outside of my comfort zone. But probably there are reasons that I do what I do. There are reasons for why I look into the things that I look at. And it's not new. I mean, people throughout history looked at the same thing and try to understand the same thing that I'm trying to understand. I guess that's part of us. That's part of who we are as a species. And I think we should keep going with that and use science to explore these things.
Thank you so much. And it was a true pleasure to talk to you today. It was really interesting, and we are sure that it is really interesting for all of our viewers who see us today.
Yeah, thank you for having me. It was a pleasure.
Civilization. Can we consider our society to be civilized? The world has come to a verge. The situation is serious. The only way out is evolutionary quantum leap. Leap from doom of consumer society into a whole new format. Creative society. What are the three conditions to become a civilization?
First one is unification. The second one is the absence of a tyrant, meaning a tsar, a king, no matter what we call him. And the third mandatory condition is possession of free energy. That's when a civilization begins to develop.
Human life is the highest value. Life without wars. Ecology restoration. Benefits for a human in various fields of existence. Instantaneous solution of all material problems. Possession of free energy. Physics of the future. Manipulation with microparticles and management of micro-world. Manipulating matter. Wasteless production. Instant healing of human body. Prolongation of human life beyond the usual lifespan. Non-invasive cosmetic corrections of human body. Almost immediate acquiring of skills on professional levels. Highly developed technologies. Flights to other galaxies. Colonization of new planets. Super civilization. And what if all this is just a beginning?
The creative society is our only chance.